So students, this is the other two spectra with molecular formulas of C6H12O2 and a follow-on of the previous two examples. In this particular spectrum, what you will see is that around the methyl region of the spectrum we have a doublet, and if I look at the integration 6, 7, 8, 9, 10, 11, 12, accounting for the entire 12 protons, and the fact that this is 6 indicates that there are 2 equivalent methyl groups in this particular structure. If I go to around 4, I see there's a CH2 group here, and the fact that it's so de-shielded must mean it's de-shielded by an electronegative atom. The only electronegative atoms I have in this molecular formula is oxygen. I also have a singlet CH3 indicating that the CH3 is not next to any other protonated carbon, and then I have a multiplet CH group, a 1 proton CH group that you see here. So let's see how I can put this together, and I'm going to get some help from these two doublets. And the first thing that I'm going to note is that in order to be a doublet, a group would need to be next to a CH group. And I've got two doublets here, a doublet for the CH2 and a doublet for the CH3s that I have here. And the only CH group I have is the CH group that you see here, which means that both that grouping and these two methyls must all be joined to the CH group. So I'm going to place that CH in the middle, put the two methyl groups that are equivalent next to it on one side, and put another group here onto it in order for it to split the CH2 group into a doublet as well. And the only CH2 group I have in this structure is the one that's de-shielded by oxygen. So if I look at this fragment that I see here, these CH3 groups would appear as a doublet. It does. There's the expansion. This CH2 group would appear as a doublet. It does. Here's the expansion that you see here. The CH group would be a multiplet because it's next to 7 equivalent protons here and 2 of the OCH2 group, so that would be a multiplet that we see here. I also have another CH3 group that is a singlet and not next to any other protonated groups. So if I take this group and that group together, subtract it from my molecular formula, I have 1, 2, 3, 4, 5 carbons, hydrogens 3, 6, 9, 10, 11, 12. I only have one oxygen here. 6 minus 5 is 1 carbon, no hydrogens, 1 oxygen. Again, that can be due to a carbonyl grouping to link the CH3 together with this fragment. I can't link anything to this carbon because I already have 4 bonds here, the CH3, the CH3, the OCH2 and the hydrogen. 4 bonds around that carbon. I have another point to attach to that oxygen, so I could now join the CH3 at one end of the carbonyl, the OCH2 on the other end of the carbonyl, which is linked to a CH, which has 2 equivalent CH3s. So this is the particular molecule for this spectrum. And then the last one, also with a molecular formula of C6H12O2. And if I look at this particular spectrum, it looks quite simple and fairly easy. it needs some thinking about because I only have 4 protons here and I have 12 protons here. But remember that these are relative. So I could have, in effect, 2 of that and 2 of that, so 6 is to 2, which would give me 8, still not 12. Or, if I multiply each by 3, 9 is to 3, which would give me 12. So if I have 9 is to 3, because remember these are relative values, that would mean 3 CH3s, 3, 6, 9, and 1 CH3 here. So if I look at this structure, both are singlets. So each of these CH3 groups are not next to a protonated carbon. So let's put the 3 groups next to a carbon atom because they're not next to a protonated carbon, so there must be something else here. The CH3 group must also not be next to a protonated carbon because it's a singlet, so I can put the other CH3 group here. And then I can now subtract these 2 fragments from here. Note that none of the protonated groups are next to the electronegative oxygen atom because otherwise I would get peaks here, and I don't. So I end up with 1, 2, 3, 4, 5, C5, H3, 6, 9, 12. No oxygens. I end up with C and 2 oxygens. So to get a fragment like this, to join that structure together, I need something like that. Now what if I join this group with the oxygen to this CH3? That would mean that this CH3 would be shifted to somewhere around 4. So I can't put the oxygen next to the CH3 group here. I would need to put the oxygen next to this carbon because we don't see any protons on this carbon. What if the carbonyl group was next to this methyl group? It would be shifted to somewhere around 2, and that's where this singlet is. So I can put those 2 groups, join it together here, and it means the CH3 group would be joined to a carbonyl group, joined to an oxygen, and I can put this entire CH3 groups on the structure, and you'd end up with a structure like this. 3 equivalent methyl groups that you see here in 1.2, and the CH3 group de-shielded by the carbonyl around 2. So I hope you enjoyed this series of solving NMR spectra. Go through each one carefully, see if you can do it for yourself, and have some fun.